Hello everyone, welcome to the Material Science Tutor. In this series, I'll be looking at material selection in mechanical design. This course is usually taken in your third year or your fourth year mechanical engineering or material science program. So in this course, I'll be looking at all the exercises in this textbook, Material Selection in Mechanical Design by Michael F. Ashby. So instead of going through the course conceptually, I am assuming that most of you watching this video are taking this course in your different universities. So I'll be teaching this course like a teaching assistant, whereby I will solve all the questions in this textbook, in the Appendix E of this textbook. There are 5 different appendices that you need for this course. They are Appendix A, B, C, D, and E. So for this course series, I'll be using only Appendix A, B, and E. In Appendix A, what you will find there is the material properties. Material properties. So all the properties of materials from metals to ceramics to composites are found in this appendix. Appendix B is related to all the formulas that you'll be needing for this course. So depending on where you're watching this video from, usually in North America, professors provide formula sheets related to any engineering course. But in Africa and some parts of Europe, no formula sheets are provided, so you have to memorize all the formulas. So depending on where you're watching this video from, make sure you follow whatever that is outlined there. Then Appendix E comprises of what? All the exercises. So with this, we can now jump into the course. I'll start solving all the questions from this course, starting from the question from chapter 3. Okay guys, let us dive right in. If you look at the question on the screen, this is E 4.1, which is the first question for chapter 3. I will not be looking at questions related to chapter 1 and chapter 2 because those questions are more theoretical based. I'll be focusing on questions with more calculations in them. So let us start. You can pause this video to look at the question. So looking at this question here, we see that it says that a cantilever beam has a length of what? 50 millimeters. So we can draw a cantilever just to make sure you can visualize it. So a cantilever has a length of what? 50 millimeters. And it has a width of B equals to 5 millimeters and a thickness of 1 millimeter. So let's visualize the cross-sectional area like this of what? 5 millimeter breadth and 1 millimeter thickness. It is made of an aluminum alloy. It is now asking by how much will this cantilever deflect if a load of an end load of 5 newtons is placed on it. So an end load means it is loaded around here of 5 newtons. So they told us to calculate what? By how much it will deflect. Calculate what? The deflection, which is something like this. How much the beam will deflect if you load this beam. So they told us to use the data from Appendix A4 and Appendix B3. So A4 is for like material properties. So they told us to find the Young's modulus, and Appendix B for the formula for what? Deflection. So if you go through the appendix, you find out that from Appendix B, from Appendix B, deflection D is equals to FL raised to the power 3 divided by 3EI, where F is the force acting on the cantilever, L is the length of the cantilever, E is the Young's modulus of the material, which is aluminum alloy, and I is the moment of inertia. So what is moment of inertia? Moment of inertia is the force, is the ability of the beam of the cantilever to resist what? Deflection. The ability of this beam to prevent itself from bending or deflecting. So that's what I, the moment of inertia, I is. And the formula for moment of inertia I is equals to BT thickness times 3 over what? 12. That's the formula for moment of inertia. So this is the moment of inertia. Also from Appendix A, you can find out that the Young's modulus E of aluminum alloys is equals to 68 to 82 gigapascals. So if you have a range, because aluminum alloy is not a single material, it's a range of materials. That's why you have a range of what Young's modulus. So all we have to do is find the average of this, which is 82 plus 68 divided by 2, which will give us what? 75 gigapascal. So now we can now use all the information that we have and solve for what? The deflection. But one thing you have to make sure that all your formulas are in the same unit. So that's why we have to convert what? Gigapascal to what? Newton per millimeter square. So 1 gigapascal is equals to 1000 Newton per millimeter squared, and 75 gigapascal is equals to 75,000 Newton per millimeter squared. Now we have this, we can now solve for our deflection. But in order to solve for deflection first, we have to solve for I, where I is equals to the breadth, where I is equals to the breadth, which is what? 5 millimeters times 1 raised to power 3 divided by 12. And this will now give us 0.417 millimeter raised to the power 4. Now, since you have the formula for, you have the value for I, you can now calculate deflection. And your deflection is now giving us F, our force that is acting on the beam is what? 5 newtons. 5 newtons times L, the length of the beam, which is what? 50 raised to the power 3 divided by 3 times our E, which is the Young's modulus, 75,000 times I, our I, which we have already calculated as what? 0.417. This will now give us what? 6.6 millimeter as the deflection. So the deflection will now give us 6.661 millimeter. This means that loading a 50 millimeter cantilever made of aluminum alloy at 5 newton at the edge will give us a deflection of what? 6.661 meter. So if you have any question, make sure you just ask in the comment section. Now we can go straight to the second question. Okay guys, let us move on to question 2. So you can take a moment and read the question. But here it says that a spring that is made from steel wire and the diameter of the wire is 1 millimeter, and the spring that is made has 20 tons in the spring. So let us draw and visualize what we are talking about. So we have a spring. So this has to be consistent, right? So it is made from a steel wire that has a diameter of D is equals to what? 1 millimeter. And it has what? 20 tons. N is equals to what? 20. It has what? 20 tons. And they say the radius of the tons, that means the radius of the tons is what? 10 millimeters. So if you have a ton that is like this, 1, 2, so consistent radius. So the radius R is equals to what? 10 millimeter. So that's the radius of the spring. So they said, how much will the spring extend if you add a mass of what? 1 kg. If you add a mass here of what? 1 kg, by how much will it extend? It's like the former question that we did. How much will it deflect? This is how much will it extend. So this is straightforward as well. They told us to get the formulas. Like assume that the shear modulus is given by 3 over 8 E, where E is the Young's modulus, and they told us to get the formula for, the extension of this spring, right? So the formula for the extension of this spring is given by what? U. It's given by U, which is equals to 64 F arrow raised to the power 3 and divided by G D raised to the power 4. So F is the force acting on this spring, which is based on the load, right? R is the radius of, like we said, the radius of each coil. N is the number of turns. G is the shear modulus of the spring, which is related to what? The Young's modulus. And D is the diameter of the wire, we already have all these formulas, everything that we need for calculating. All we need to do is what? Get G, whereby they said what? G is equals to 3 over 8 E. And so this is the formula for G. If you go to appendix A4, you see that E is giving us, E of stainless steel is giving us what? 199.5 gigapascals. So if you want to convert this thing to a standard unit, since we are working in what? Millimeter, to convert this thing to Newton per millimeter squared, it's just multiply by 1000, right? So all we have here is 199,500 Newton per millimeter squared. So that's our E. So right now we have our formula for E, and we know that the force acting on this material is what? Mg, which is what? Mass times what? Acceleration due to gravity. So converting this, it will be 1 times what? 9.81, which is equals to 9.81 newtons. That's the force acting on this body. Right now we just have to calculate G. We just have to calculate U, and U is now giving us is equals to 64 by 9.81 in newtons times what? Our R, which is what? The radius of each coil, which is what? 10 raised to the power 3 times the number of turns, which is 20, all divided by 3 over 8 times our Young's modulus E, which is what? Which we've calculated as 199,500 times 1 raised to the power 4. So U will now be equals to 167.84 what? Millimeter. So that's our extension. So the extension of the spring is giving us what? 167.84 millimeter. So that's this for this question. If you have any question, don't forget to drop it in the comments. Let's go to the next one. Okay guys, let us move on to question 3. So for this question, they said a thick wall tube has an inner radius of 10 millimeter and an outer radius of 15 millimeter. So let us just draw a tube. So you have a circle with an outer radius, another one with an inner radius, and you draw your lines. So this circle has ROI of what? 10 millimeter, and this one has RO, which is what? 15 millimeter. So that's our ROI and what? RO. So they said it is made up of polycarbonate material. So the material is polycarbonate. What is the minimum torque? So they told us to find the torque that the tube can carry without yield. So the minimum torque, that's what it's asking for. The minimum torque that it can carry without yield. So it will not get to the yield point. It will still be before the yield point in the elastic region. So what is the minimum torque it can carry before it yields? So they told us to retrieve the mean yield strength of polycarbonate from appendix 5. So this is why you need those appendices if you're trying to solve all these questions. So the formula, if you go through the appendix, you see that the formula for torque, T of F, is giving us K rho Y divided by 2R. 2R naught. R naught, which is K, is a constant. K is a constant given by K is equals to pi divided by 2 brackets R raised to the power 4 RO, which is outer radius, minus inner radius raised to the power 4 inner radius I. So that's the formula for K. So they told us to find what? Torque. This is what we are looking for, the torque. So everything here in this chapter is straightforward. So first we have to calculate for K. So K is now equals to pi divided by 2 bracket, our outer radius is what? 15 raised to the power 4 minus 10 raised to the power 4. Then our value for K, if you calculate it, is 63813 point. So this is 3.6 millimeter raised to the power 4. So this is our value for K. So the next thing is to calculate what? TF, which is torque at failure, which is torque, which is given us, we just plug in our values to this formula, which is 63813.6 times 64.5. So this 64.5, how did we get 64.5? 64.5 is given by the yield strength of PVC. So the yield strength of PVC, yield strength is given by 64.5 megapascal. and megapascal, and if you're converting megapascal is equals to 64.5 Newton per millimeter squared. So that's why we have this value here, 64.5 Newton per millimeter squared, divided by 2 times initial radius of what? 15. So since you have your initial radius of 15, your TF will now be equals to 137,199.24 Newton millimeter. So that's your torque. So if you have questions, put it in the comment section. I'll get to you. Moving on to the next question, 4.4. It says a round bar has a diameter of 20 millimeter, but it has a shallow circumferential notch. What does a notch mean? A notch means that a straight bar has like a dumbbell shaped bar. So instead of having a straight bar, you have a dumbbell shaped bar. A bar that is like this and has a notch that makes it like a dumbbell. You get what I mean? A dumbbell. And it has a notch depth. The depth of the notch is what? C is equals to 1 millimeter. So depth of the notch here is what? C is equals to 1 millimeter. And the radius of the notch here, R, is equals to 10 micron. That's the radius of the notch. And they said if the bar is loaded by F, so if you're loading the bar on tensile loading, if there is a tensile loading of the bar F, and the yield strength of this material, the material is made of what? Low carbon steel, and the yield strength of this material, yield strength is equals to what? 250 MPa. And they're asking for a value of strength, the strength of the nominal strength of this material where yield will first commence. So which value of nominal strength where yield will first commence? So we're going to find the relationship between maximum yield strength and regular yield strength. They told us to use the stress concentration estimate of appendix 9 for appendix B9. So the relationship between maximum yield strength over nominal yield strength is equals to 1 plus alpha divided by C over R, all raised to power 1 divided by 2. So this is the relationship between maximum yield strength and nominal strength, maximum stress and nominal stress. So this is the relationship between what? Maximum stress and nominal stress. So they are now asking us what will be the nominal stress when maximum stress is equals to what? The yield strength. So this will now be equals to what? Yield strength Y, and they are asking us to find what? This is what we are looking for. So we'll just change. So we now make this subject of the formula. We now have what? Nominal stress is equals to, we are now replacing this with what? Yield strength. Instead of maximum stress, we are now replacing it with yield strength, which is equals to 1 plus alpha raised to power C divided by R, or divided by 1 divided by half. So when you have this, you can now break this equation down, input your values and what? Solve. So when we have something like this, we now have what? Stress, which is the nominal stress, which is equals to our yield strength is equals to 250 MPa. So converting 250 MPa to Newton per millimeter is equals to what? 250 what? Newton per millimeter. So 250 divided by 1 plus, also the value for alpha, if you look at your appendix B9, the value for alpha is equals to what? 2, because this is what? Torsion, and this is what? Tension, not torsion. So the value of alpha is equals to 2. So 1 plus 2 times, we are looking for C, which is C is equals to what? Our depth of our notch, which is what? 1 millimeter, divided by radius of the notch, which is what? 10 micron. So converting it to millimeter, you have what? 0.01, or raised to power 1 divided by 2, or raised to power 1 divided by 2. Now what you have, what? Our nominal yield strength is now equals to 12.5 what? Nanomillimeter squared. So this is straightforward. So everything in chapter 4 is straightforward. Okay, for question 5, take a second and look at this question. So this question says a window. So we have a window like this. It's made up of a PMMA, which is acrylic, and the frame of the window is made up of what? Low carbon steel. So this material PMMA has what? A higher thermal expansion coefficient than low carbon steel, which means that once this one PMMA, when the temperature falls to what? -20, it will shrink. It will try to shrink. But because of it is shrinking faster than low carbon steel will tend to prevent it from shrinking, causing what? Tension in this material. So now that we have understood the phenomena happening here, we have understood everything happening here, we can now go ahead and read the other question. The question asks us to find what stress does it carry at -20 degrees C. So when you change the temperature from room temperature to -20 degrees C, what stress does this material PMMA carry when you change the temperature? So this relationship is given by the formula already provided. The relationship have already been given to us. The relationship that helps us calculate what the stress carried by PMMA is given by this stress. Stress is equals to E changing E over 1 minus Poisson ratio. So this is the Poisson ratio. Why this is the biaxial strain caused by what? The difference in temperature. Why E is what? The Young's modulus of what? PMMA. So in order to calculate this, we need to find the formula for this. In order to find the formula for this function, we'll use what? Table B.5 in appendix B.5. So the relationship is given by what? This relationship is giving us changing thermal coefficient times changing what? Temperature. So in order to break this down, changing E is equals to thermal coefficient of what? PMMA minus thermal coefficient of what? Low carbon steel. Of what? Low carbon steel times what? Changing what? Temperature. In order to do this, if you look at, so this is the formula that we are looking for to calculate what? This function, the biaxial strain, right? So in order to calculate this, we need to go to what? Appendix A7 in order to get the values for thermal coefficients for PMMA and low carbon steel. So the thermal coefficient for PMMA is giving us 117 times what? 10 raised to the power -6 per degree C. Then for low carbon steel, we have what? 12.3 times 10 raised to the power -6 per degree C. So calculating this, we now have what? Changing biaxial strain is giving us 117 times 10 raised to the power -6 minus whatever we have here, which is 12.3 times 10 raised to the power what? -6. 12 times 10 raised to the power -6. Everything times what? The change in temperature, which is what? 20 minus 20. So if you now solve for this, you will have what? The change in biaxial strain is now equals to 4.19 times 10 raised to the power -3. So now you have this you now calculate with this. Since you already have this function, you now calculate what? For what? The stress. The stress is now giving us the Young's modulus. Young's modulus of Young's modulus of PMMA is giving us what? 3.02 gigapascal. And now the stress is now equals to, with this formula over here, we can now calculate as 3.02 times 10 raised to the power 9, which is gigapascal. We're converting to what? Newton per meter squared, times 4.19 times 10 raised to the power -3, all divided by 1 minus 0.33, which is the Poisson ratio given to us in the question. So stress is now equals to what? 188. If you punch it out, if you just solve for stress 1.886268 Newton per meter squared. If you want to convert, you can also you divide by 10 raised to the power 6, which is stress is now equals to 18 point. So it should now be 18 0.89 megapascal. So this is your answer for question 4.5. If you have any question, let me know in the comments from question 4.6 from part 2. Thank you very much.